Hi class, we're going to look at two different types of collisions today, elastic and inelastic collisions. In our first type of collision, we have a basketball that's falling towards the ground. It's going to move. We see that it starts with some kinetic energy because it's moving and some potential energy due to gravity. When it hits the ground, it compresses a little bit. That energy that we had at the beginning has now become stored energy in the compression of the basketball. So we now have potential energy or spring energy. There's not a spring inside of there, but it's stored inside the compression of the air molecules. So it's acting a little bit like a spring. After the ball hits the ground, it's going to bounce back up, and that spring energy is going to turn back into kinetic energy and back into potential energy. Let's contrast this type of collision with the second one. If we had a piece of clay here, which is what I have, that's falling with the same amount of kinetic and potential energy as the basketball, when it hits the ground, it's going to squash and it's going to turn into thermal energy. So our kinetic and potential energy has turned into this thermal energy here. The thermal energy isn't going to transform back into kinetic and potential energy. That's very difficult for thermal energy to do. It's going to stay as thermal energy. And so we can never reclaim that kinetic and potential energy that we had at the beginning, which we were able to do when we had the basketball hitting the ground. These two types of collisions are known as elastic and inelastic collisions. In an elastic collision, some or all of the kinetic energy is transformed into elastic energy during the collision, but then later on it's transformed back into kinetic energy, or this really should say gravitational energy. Okay? In an inelastic collision, some or all of the kinetic energy is transformed into thermal energy, and that never gets transformed back into kinetic energy. So I want to show you two examples here, two more examples of an elastic collision and an inelastic collision. So here's our elastic collision. You've seen these before. Newton's cradles. All that kinetic energy that we have right before it hits the ground, hits the ball here, is transformed probably momentarily into some compression inside each ball. So we have some spring energy stored, but then that spring energy is turned back into kinetic energy as this ball goes flying off to the other side. Okay? Alright, so for the most part, the kinetic energy before it hits is equal to the kinetic energy after it hits. Now let's contrast that with this. Got our two cars moving. Okay, so before the collision, this red car had a lot of kinetic energy. It hits the wall and it stops. All of that kinetic energy is not going to cause the car to bounce backwards. It's been turned into thermal energy. Over here in this car, we do have another large amount of kinetic energy. It hits the wall. It turns momentarily into a little bit of kinetic energy as this goes flying up, but all that kinetic energy is going to eventually turn back into thermal energy as the car gets heated up, or into another form of elastic energy that's used, or internal energy that's used to break bonds between molecules in the car. By the way, that goes for this one as well. That kinetic energy not only becomes thermal energy, but it's also used to break bonds between the molecules inside the car and cause it to crumple. All right. So in an example of an elastic collision, before you may have two objects moving towards each other. They both have momentum, they both have kinetic energy. Afterwards, they've bounced off of each other. They're bouncing away. We know that before and after, the total momentum of our two objects must be constant. So momentum conservation applies. And we also know that because this is an elastic collision, the total amount of kinetic energy that we start with must be equal to the total amount of kinetic energy we have afterwards, even though in between some of this kinetic energy became elastic energy. It's all been turned back into kinetic energy by our after situation, and so these two quantities must be equal. Let's contrast this with an inelastic collision where the two objects are coming towards each other. They hit, And in this case, they continue moving to the right, but some of the kinetic energy we started with here has turned into thermal energy of the inside these two objects. The only We know that momentum still is conserved in this case, so our total momentum before equals our total momentum after. However, we also know that these two objects, since they're stuck together, have the same velocity afterwards, which allows us to simplify our momentum conservation equation into something that we can solve if we know the initial velocities of the two objects. Notice I didn't write down an expression for kinetic energy because we would say that the kinetic energy that we begin with is equal to some kinetic energy at the end plus some thermal energy. It's very difficult to calculate how much thermal energy that is if we don't know how much kinetic energy we have at the end. So our energy expression isn't going to help us solve this problem at all. Okay, so today we talked a little bit about elastic collisions. They're collisions in which we defined an elastic collision. It's where kinetic energy is temporarily transformed into elastic energy, but is later turned back into kinetic energy. And we also defined inelastic collisions. That's when all or some of your starting kinetic energy is transformed into thermal energy or internal energy, like we saw in the car accident when some of that energy is used to change the shape of metal or shatter glass or break bonds between molecules. And that energy is never going to return back into kinetic energy. Okay? Not all collisions are one or the other. You can have some where most of the kinetic energy is reclaimed at the end, but some of it has turned into thermal. So there's a mixture. We call some collisions perfectly elastic, which means that none of the energy is lost to thermal energy. And then we also have collisions that are perfectly inelastic, in which all of the kinetic energy is turned into thermal energy. Okay, thank you very much.